We're going to have some additional folks join us, I'm sure. Here they come. But I want to welcome you. I'm Brian Winkle, the director of Simiode. We have with us today Lee Noble, who's a technical director, who is here to make sure that absolutely nothing goes wrong. We have our speaker, Sami Kanderian, and we have a number of you, and we're welcoming you. This is the first of a three-part series of webinars based on talks from our Simiode Expo conference that we held earlier. And we thought that these would be expandable from a 20-minute talk to maybe a 90-minute webinar. The first one is about a marvelous piece of software that allows you to do modeling. The second one is about another marvelous piece of software. And the third event is on the 1st of May. It's a group of faculty who are trying to get ethical reasonings into mathematics courses through modeling. And if you registered for this one, you have gotten permission to come to all three of these. And this information is online so that you could find it without any trouble. So without further ado, I want to introduce Sami Kanderian, who's out there in Germantown, Maryland. Sami is a consultant in the biosphere. He's an engineer, and he developed a marvelous piece of software to help him in his profession, and was kind enough and reached out to pedagogical colleagues like many of us, and is here to talk about its uses and what you might be able to do with it. And so I'm going to turn it over to him and ask him to share the screen. And we're going to go for about 90 minutes so we can have time for questions. We may have time at the end for additional questions. But one of the things you should know is that the two software packages, the one we're talking about today and the one we're talking about next week that Eric is going to lead, are free, downloadable, playable, usable. And so even if you're not up to speed with every single thing that goes on here today, you'll be able to gain that. And this recording will be posted in our YouTube site, and we'll let you know that it's there in case you want to refresh it. So I'm going to stop. Sami, share the screen and take it away.
All right. Thank you. Thank you, Brian. Let me see if this works. Do you see a screen that says WikiModel?
Yep.
All right, let me make it, let me enlarge it so it's the whole screen. All right. Well, thank you, Brian, for the opportunity to present, and I really appreciate that. This is my third presentation with Simiode, and I've enjoyed the first two, and I'm sure this one will be no different. And I'm looking forward to this one because this one is hopefully going to be a little more interactive than the last two, that will allow the participants to try the software during this webinar. So I'm excited about that. So I'm here to present about my software, which I call WikiModel, because you can create and simulate, fit, and share mathematical models pretty quickly and easily. And my website is if you just go to your browser and you type in wikimodel.com, it'll take you there directly. And there are some other sublinks that talk about what it is and some application instructions, and I'll bring those up later. So why did I create WikiModel? So as Brian mentioned, I'm an engineer, and I in the biomedical space, and in my career, I needed to do quite a bit of mathematical modeling, and a lot of the models also were differential equation based models. So they were sets of ordinary differential equations, or ODEs. And so, a lot of people can create models and simulate them and fit them to data. Now, to do that today, you'd have to be a programmer. So you have to know how to do some programming, and you also have to know the mathematics, and you you obviously then you have to know how to code, and with differential equations, you actually, there's an extra additional effort for coding where you have to enter your differential equations in a separate function, and then you have to call that function from using an ODE integrator. So with models that are comprised of differential equations, there's a little more effort involved. And the other thing with ordinary differential equations is if you add a disturbance to the ordinary differential equations, you have to start and stop the differential equation integration routine and change the initial condition every time you have a new input to your model. So that also requires additional coding. And then also for my work, for any work, really, it's important to be able to fit your models to experimental data, because that that gives validity to your model. And then you can also re-simulate your model with different inputs and see if they replicate experimental data again. So this whole cycle takes time, and it takes knowledge of a programming language and a lot of effort. And so I've reached out to Brian because he's in academia, and he works with a lot of undergraduate students. And I love coding. It's my bread and butter, and I don't discourage it at all. On the contrary, I encourage it. But if you're a freshman and you're trying to learn differential equations or mathematics, and you're a professor and you don't want your students to get bogged down in the implementation, that's why WikiModel was created. So so again, about my work, I started my career in diabetes technology, where I was optimizing for type 1 diabetes. I was optimizing open loop and closed loop control. So in closed loop control, you have a glucose sensor that's measuring your subcutaneous glucose that is closely follows your plasma glucose, and then on every 5 minutes or every 1 minute, you can change the insulin delivery profile to bring your glucose in control. So when your glucose goes high, you deliver more insulin. When it goes low, you cut back. And when you take meals, you give additional insulin. So what I'm showing you is sort of the background of WikiModel. Is when I started working, I didn't have WikiModel as a tool, and I did a lot of programming, which was fine, but it required a lot of upfront work and a lot of time to do. And if I had WikiModel at the time, it would have expedited the process. And so when I built WikiModel, it was primarily, I just had this example or one example sort of implemented that was hard coded. And then I said, you know what, it would be nice if I could generalize it so that a user could enter in their own customizable set of equations, and they can be differential equations, or they can be analytical equations, and so on and so forth. So again, this is sort of the background of why I created WikiModel. And here you could see on my left figure, I have one patient, one type 1 diabetic patient, and the top graph is their the points. The red points are sort of their plasma glucose measurements. And you could see that my simulated glucose is this black line, which kind of replicates that, which is fit to the data, and that's why it follows the data nicely. So one of the inputs to my model is insulin delivery, and you see that in the shaded region in this second plot here. And when you deliver insulin, it shows up in the plasma, and the experimental measurements for plasma concentration are these blue dots. And then I have my modeled plasma insulin in the black line, and that's also a simulated output. And so you could see that my model for plasma insulin based on the input delivery is follows the data quite well. And the last thing I have that's also an input to my glycemic model is the carbohydrate, or basically the number of grams of carbohydrate, or essentially all the meals or drinks um, that were ingested by the patient, and that's what you see in the last plot. And so, you know, to do this, I had to do a lot of coding, and I had to also fit the simulated output to experimental data points, whether that was insulin or in the end glucose. And so this is what you see on the left is one patient, and I sort of did it to 10 patients. And if you average, you know, each patient is fit first and then averaged, and what you see at the end is sort of on the right, which is the average of 10, and you could see that the modeled output follows the data. And so why is this important, though? Why was this important in my work? So if you can replicate experimental data, you can then what you could do is you could change the input strategy and say, well, you know, with type 1 diabetes, what they try to do is lower the peaks and raise the nadirs so that there are no hypoglycemic events. And so what you can do is you can change your closed loop insulin delivery strategy, or, you know, how much how much insulin you fuse on a minute to minute by basis, and it's a closed loop algorithm that decides what you're going to deliver. And by changing your strategy, you could see if your modified strategy gives you better glycemic control or worse glycemic control. And the advantage with using these ordinary differential equation models is you can test out your new controller before you try it out on a patient, because if you try it out on a patient sort of without knowing a priori how it might behave, that could be dangerous to the patient. And it also would require a lot of clinical trials before you get to an acceptable solution if you weren't able to model and sort of you know, test out your closed loop controllers in silico or on the computer. And clinical trials, you know, cost a lot of money and take a lot of resources. And most importantly, you want to have an idea of how it affects the patient before you try it. And so what I'm showing on my next slide here is a modified strategy. You know, two different closed loop strategies. One is full closed loop. One is a hybrid closed loop or semi-closed loop where the insulin is still manually given with meals, and the red one is fully automated insulin delivery where everything is determined by the algorithm, and there's no open loop delivery. And what you see is on the left plot are the results for the new simulated output based on my model that I derived with the parameters that I fit from a prior clinical experiment. And what you see on the right is a clinical trial with real data based on this modified strategy. And you could see that the clinical output matches the simulated prediction pretty well. And this is important because it's an independent validation of the model. So all this to say is, you know, that's what WikiModel allows you to do, except that instead of just fitting it to a you know, a predefined fixed model, I've allowed the user to decide what the model equations are. So if you know the equations, you know, just like they appear in a textbook, you just type them in, and you know, and you if you have parameters for the model, you could type those in with the values. And once you do that, you could just simulate it, and you can also enter in experimental data and fit your models to the data to get parameter estimates, right? So one thing I will say is, which is also nice about the WikiModel software, is it doesn't have any downloads or installation. You just go to the www.wikimodel.com and you register for an account, and then you will, if it's your first time logging in, it will send you when you do the registration step, it'll send you an email to confirm that you are in fact a real person with an email address, and it'll allow you to log in and you'd be ready to go. So in part of this webinar, we'll go through that process. So again, with WikiModel, it's custom. In other words, you decide what the differential equations are, and you can type them in. And it'll handle any number of differential equations and or analytical equations, and it'll simulate, and the results are simulated and plotted on the screen, and it can handle discrete inputs or disturbances to the model, and it will seamlessly fit your model to experimental data. And the experimental data can happen at different time, you know, at sparser times than your simulation, which can be more, which is in a more frequent time scale. And then you, as I mentioned, you can fit the model to experimental data, and it'll automatically figure out if it requires linear or nonlinear least squares. And then once you've created your model, you can save your model to use later on. You could save it privately, so only you have access to the model. You can save it to a group of other users. So if you're a professor, you could create a group of other users that have registered for an account and add them. Or you could share them to the public so anybody can see. Okay, so what I was going to do next is sort of bring up an example and simulate that. So similar to sort of the a pharmacokinetic pharmacodynamic example with glucose and insulin. Here I picked an example from Simiode, and I'll bring up sort of the PDF there. So in this example, what we have is a two-compartment differential equation model where a dose of LSD is administered to the patient as an IV drug, and this two-compartment model describes the plasma space, which is at the bottom, and the tissue space, which the drug goes in between the plasma and the tissue. There's the LSD can go in and can leave the plasma and go into the tissue, and vice versa, can leave the tissue and go back into the plasma, and eventually the drug is eliminated from the plasma space. So that's what the arrows represent, the transport of LSD in between compartments. And this initial one here is the dose. And when we say tissue, we're specifically talking about the brain. How does it affect the brain? So all this information is available on the Simiode website, also for free. And if I go back to my slides, if I go back to my slides, basically, the building block of a pharmacokinetic model are these compartments, and then every compartment is described by a differential equation, right? Where you have these rate constants going in and out of each compartment, and all the time constants entering or leaving the compartment has a minus sign in front of it, and then you multiply that by the concentration of that compartment. Then you have to add the rate constants leaving the compartment multiplied by the concentration of the drug in the compartment that they're going to. So these time constants are in units of 1 over time, so 1 over hours in our case. So what I'm going to do is bring up the implementation of this model in WikiModel. Now I've entered it in already to save us some time, and I'm going to bring that up now. I forgot to mention at the beginning of the talk that I don't want to do all the talking, and it's meant to be interactive. So if you have questions, you don't have to wait until the end of the talk. You can ask it at any time, and I'm happy to answer any questions. So what you're seeing is my web page in Google Chrome, but it works in any web browser. You see the address is wikimodel.com, and I already have the model implemented. And as I mentioned, sort of each compartment is represented by a differential equation. Now, a little bit more about the page. On the left-hand side, you'll see all these models that mostly I have saved and created that's available for public use. So you could sort of go in and try this out. If you log in, you can search for LSD. And let me see if I do that. It will come up. Let me reload this page really quick just to show you. So here I have it's a different model comes up by default, but you can see that I'm logged in, and if I type in LSD and hit enter, you'll see that it shows up here, 2-compartment LSD model. And if I click here, it'll kind of expand it out so you could see it better. But if you select the one that you're interested in, it turns blue, and then you hit load selected model, and then you can see that, oh, here's the model. So as I mentioned, each compartment is described by a differential equation, and there are these rates that enter and these rates that leave, and we have the plasma compartment. So this is a plasma concentration, and you also have the tissue compartment or the brain compartment, and there's a constant that is important for this model, and it's the ratio of the distribution volume of the drug in the tissue over the volume in the plasma, and that ratio is about 0.7. So, and that comes into play here. And for more details, you can find this PDF on the Simiode website, and it'll have the description in more detail. Of course, when you're simulating ordinary differential equations, you need to type in the initial condition for each differential equation. Now, this value is sort of the initial concentration in the plasma, and that's estimated, because through the dose that's administered. Based on the dose, based on the weight of the patient, you can estimate the volume of each space. You can estimate the plasma volume as it's proportional to the mass of the patient, and based on that, you can estimate the initial concentration of the drug. I think the units are in nanograms per. What is the units in? Let's see here. Nanograms per I think it's per ml. Yeah, nanograms per nanograms per milliliter. So and in this model there are three time constants, and the units are in 1/hours. And so what you do is you after you type in the three equations, you type in all the parameters, and when you type them in, I'm going to type in different numbers so I'm going to type in 4 and maybe 3, and let me get this 0.5. So you can, before you hit simulate, so this is the simulate button. Before you hit simulate, you have to go to the plot. You have to go to the plot tab and tell it what you want to plot. So in our case, okay, my x-axis is time. I want to plot my plasma, my simulated plasma, that's P, LSD concentration in the plasma, And I also, in another plot, my second plot, I want to plot the tissue. So this is the LSD concentration in the brain versus time. And you'll see that I've added two other plots. And what these are is data, the experimental data. So if I go to the data tab, this data table, you'll see, is for every, there were an experiment run with 5 patients, and the plasma concentration was measured in each patient over time, over the period of 8 hours. And also, in this experiment, users were, or patients were given a test to see their cognitive ability, and their relative scores over time was also measured. So if we go, if I hit simulate, so let me hit simulate. I hit simulate, it says, okay, the simulation completed successfully in 0.005 seconds. So if I look at the simulation, this is what the LSD concentration in the plasma looks like over time. It's this sort of purple line. I picked P for purple. And I picked, this is actually the concentration, the resulting concentration of LSD in the tissue or in the brain, in the brain. And you could see that obviously, since before we give a dose, or at the time that we give the dose, there is no LSD in the brain. And as the drug gets transported from the plasma compartment to the tissue compartment, it goes up, but then it starts to leave the tissue compartment and go back to the plasma. So then it goes up and then comes back down, and then eventually it clears from the body. So over time, the concentration of LSD in both compartments drops to 0. So as you see, I've plotted 3 graphs. This top graph is the plasma simulated. Now, what I plotted in the black points is the experimental measured plasma concentration that was taken over that 8-hour period. And what I plot in the last plot is this cognitive score that you could sort of see starts high, goes low, and then comes back up. We'll talk a little bit more about that later, but again, was sort of one of the nice things about this application is you could fit, like, we could fit the simulated plasma to the experimental plasma. So what I want to do is I go here and I pick P as my plasma concentration, simulated plasma as my fit variable, and I want to fit it to data P1. So let me make sure that I'm plotting the right, I'm plotting the right stuff. Okay, so once I select what simulated output I want to fit to what data set from these 2 dropdowns, and you can see you don't type anything in, it sort of pre-populates this dropdown, and you just kind of pick what you want. Then once you do that, you can then hit fit. Now, before I hit fit, you'll see that these parameters that I chose, 4, 3, and 0.5, don't really fit the data well. It's, it's reasonably close, but it's, it's underestimating, right? So I don't have the right rate, rate constant. So let's see what happens if I hit fit. So when I hit fit, I don't know if you noticed, but my simulated output is changed now. It moved sort of the curve up, and you could see that it goes through the data points a lot better. And the resulting tissue profile is also shown here. And so that's what's really cool about this is, we entered in a set of custom equations from an example that that Professor Winkle came up with. I think he found it from the literature, and he decided, hey, this is pretty cool. I'm gonna model this scenario that was published in the literature. And so this I asked him for a neat example, and he came up with this. And here's the simulated result, and here's not just the simulated result, but here's the fit parameters to the experimental data. And you could see these are the fit values that are, are different than what the initial guess was. And I can, if I hit this copy fit value to parameter value, I can fit it again, just to make sure the solution converged, So if I hit fit again, it didn't really change, which means that it was pretty sure that's the right answer. So there you have it. So here we've gotten the result. And going to the last thing where you see the score, you notice that the score is inversely proportional to the amount of LSD in the brain over time, which makes sense, right? So it goes down, comes up, and that's kind of interesting. So you can actually have another model that just fits the resulting tissue at those time points with the data, and you'll see that linear relationship. And what you can also do is you can sort of, instead of fitting plasma concentration to the experimental data, you could fit the scores. You can add, I actually have that saved in a different model name, but you can have you can have another equation that describes the relationship between score and the tissue concentration as a linear relationship. And you can actually estimate the plasma concentration and the tissue concentration without actually measuring experimental plasma values, but just by using the score values, which is kind of interesting. But I won't go too much into that here. If I wanted to fit the data to another patient, so here I've got patient 1, patient 2, patient 3, patient 4. So if I want to fit to a different patient, I just have to change, P1s, all the P1s to P2. So I'm now going to do patient 2 and patient 2 plasma concentration and patient 2's score. And if I hit simulate again, and I can go to my model here, and if I hit fit, so these are the results for patient 2. So you can choose whichever patient you wanna fit by changing. Hold on, by changing it in the dropdown? Let me make sure I did that. So I actually didn't fit it to patient 2. I have to change this to P2 as well. And now I'll hit fit. So now the fit's much better, right? Because I accidentally fit it to patient 1. So you just have to make sure that you're fitting it to the right patient data. And you could see that for patient 2, the results are quite different because there's patient-to-patient variability in these rate constants, right? So we started with the initial guess based on patient 1, but for patient 2, it came up with a different set of fit values. Are there any questions so far?
Yeah, Sammy, if you wanted to add up and take the average of the patients, you could probably do that as well, right?
Right. So right now, it would be nice if that feature was implemented where I could say, hey, can you loop through all 10, fit them, and then average them, like I did in my publication, right? So right now, that feature is not there, but I will tell you what feature is there. So here right now, we've simulated patient 2. What I could do is I could go down here, and I could say, download simulated results to tab delimited text file. So if you do that, I will save it to, I'll save it to my downloads folder, or let me create a new folder. I'm going to call this LSD output, LSD output. So if it's going to save it as 2-compartment LSD model simulated results. And it's called that because that's what I saved my model name as, but it'll add the word simulated results to the end of it. So if I hit save, now if I open this folder, showing folder, if I open this file, let me open it in Excel. Excel. open, browse, downloads, where to go? I'm not sure where that was. Where did
Well,
I'll just do it this way. Oh, here it is. Temp. Oh, here I go. Open, browse. And it's a text file. So if I go, you hit next, it's a tab delimited file, but if you just hit next and finish. So what you have now is the this is the fit output because the last button I clicked was fit. So what you have is your time, your, this V ratio doesn't change. That's just a constant. So that's why that number doesn't change. But what the simulated outputs, here's the plasma concentration over time and the tissue concentration over time. This is again for subject 2. So if I do this, I can do, I can show it as a graph here and it'll match the same graph that you saw there. Insert chart, and you can see that here, right? So you've got the plasma, the plasma is the blue and the tissue is the yellow. But to answer your question, to average them, what you can do is you can do this for all 10. And I know that's a little bit, a little bit time consuming, but let's say you had them for all 10, then you can average them. And then you can also average the data. Here's the data. The data's here. And you can average the data and then plot an average plot of, the purple and the black points and the average blue line here. So it would be nice, if that feature was implemented here where I could say, hey, can you loop through all 10 and just give me each one as well as the average? That would be a nice feature to have. And maybe hopefully sometime in the future, I can implement that.
So if any of you listening, do you have what kinds of questions, if you're doing simple compartment models, what kinds of questions do you raise for your students that you think this might be useful as a prompt? Nope, silence.
So, I think what was cool about this is you can plot the tissue concentration versus the score and see that they're correlated. And I'll bring up the PDF from the Simiode website. And where is that? You could see that here. So if you plot the math, the sort of the cognitive score of the test they were performing over time, as the LSD in the brain was changing over time, you'll see that it's inversely proportional. And I think that was kind of pretty cool about this is, in the experiment, we didn't originally have this curve, which was the brain, the LSD concentration in the brain, but we could see that, oh, you can actually estimate it without knowing the experimental concentrations in the brain, because nobody's going to sample drug from the brain. That's too intrusive, right? You can sample it instead from the plasma and estimate it in the brain. And as I mentioned before, you can even not measure it in the plasma. You can have your model output be the scores if you know that there's an inverse relationship, and then you can actually estimate both the plasma concentration, LSD concentration in the plasma and the brain without ever measuring them, just by taking the scores. Now, with taking the scores, it's kind of a little hard because when you take a test, it's not instantaneous like you're taking a blood sample. So maybe the accuracy isn't as good, but it's kind of an interesting idea, and it's actually feasible. Let's see, where do I see? So I can go just take a look at the time. So it's now, let's see.
Well, let me try to get a live response from someone in our audience by asking, how many of you actually use data and do some estimating of parameters? And if your answer is yes, could you at least give us an idea of what context? Okay.
We do have a question in the Q&A. I don't know if Sammy wants to take that now or
Oh.
later. Can you see it, Sammy?
Let me see. Let's see.
Or I can read it. I can
Go
read
ahead.
it.
Go ahead.
Andrew?
Or Andrew, if he wants to read it, you're welcome to.
Oh, hi, everyone. Thanks for the talk so far. It's really interesting. So my question was, once an equation or set of equations has been put into WikiModel, is there a way WikiModel could then write Python code that we could then copy paste into Python and have the SciPy integrators work on it, kind of using WikiModel as a test bench, and then maybe that then exporting that and then looping over the 10 subjects and doing the fit each time?
That's a good question. That's a good question. So let me answer that. I understand your question now. So you're asking if you can feed the data into WikiModel through Python and have the loop in Python, send the data and get the results, and then have Python average the outputs and plot the average. Is that what you're asking?
Well, I was imagining, so students are kind of inhibited from writing Python from scratch, right?
Right.
But WikiModel is a much more friendly thing. If they
Right.
could write their model in WikiModel and then have it write Python code that the student could then copy and paste.
Mhm. So
Um,
are you asking if the Python code will do the ODE integrations and simulation, or just get the outputs
um,
and handle the
I was
outputs?
imagining it would be the code, mainly the code that computes the derivative based on the current system status.
Mhm.
And there could be a template like paste your function code here
Mhm.
and already have a little bit of stuff that will then call the integrator. But
Yeah.
I didn't mean to derail the talk here,
No,
so
that's
we
fine.
can talk about it later.
Yeah. So this code, the purpose of WikiModel is so that the user doesn't have to implement the ODE integration or fitting in
Right.
Python or another language.
Mhm.
But what it can do is, if you have lots of data, like 100 data patients instead of just 10,
Mhm.
the way that WikiModel works is there's a front end and the back end, and the two are actually separate. And the front end is basically that user interface on the Chrome browser that you see, and the back end does the computation, and the front end sends the data to the back end and gets the computations or the fit. Let me see. Let me see if I can find that. Yeah, so if I go back here, there's actually an API that it uses to send the data between the front end and the back end. And if I go to advanced, and I should write, and you can basically use Python or Java or C or whatever language you like to send the inputs, and it'll send it to the cloud and do the computations and send you the results. So if I go to advanced setting and show API content, and then click here, you'll see that, here's and I can simplify the inputs. I'm going to simplify the inputs, so whatever you send is much shorter than this. But there's a lot of stuff here because it's sending all 10 data sets every time. You don't have to send all 10 at once. You could just send one at a time. And here's the result that comes back. So basically, if you wrote your loop that sends in each data set one at a time, it'll give you the results one at a time. So I can write some instructions on how to do that. But it will not, it's not like ChatGPT where it'll say, oh, you want to do the same thing in Python. Here's how you do, here's the implementation for integration in Python. It won't do that.
Okay.
So far, what you've shown is that you can input a differential equation model, you can input the data, you can input some conjectures about the parameters, and it will use an algorithm of minimizing sum of square errors or something like that to get you the best fitting parameters. And that may be what you want as a teacher. In other words, the student has either collected the data or used the data from the literature, and this tool will allow them to build a model input the model, estimate your parameters, and validate how good it is because of your graphical inputs. So that's the main theme that we're trying to convey to those of you who are here. And I think, as Sami said, it's not ChatGPT.
Yeah.
And how many models have you got in there already that, you know, people can tap into? Because that might be easy for people to look at rather
Yeah,
than.
you know, I've got so many, and you know, it's nice that there's so many, but what's disappointing is if you look at who the creator is for all these publicly available model, it's mostly just me. You know, I have some colleagues that that are using it. That I'm working with, but mostly it's just me. So there's a lot of models, and you can search for different ones with the search bar, just as we typed in LSD. You know, I could type in projectile. You can see I've done that before here. And I've got all these projectile examples. I think the coolest one is this marble projectile with drag. But we'll talk about a few of the select examples that I think are pretty cool later in the presentation, but there are a lot of models that you can investigate here. And, you know, just like this LSD one, you don't have to start from scratch. You could start with a model that's already available to the public and play around with it. And you can actually, if you save it, you don't have to be worried that you're going to overwrite someone else's work. It will save the same copy of it under your name so that you have your own copy, and if you make changes and save it, it's going to be your own copy.
Will it be public or private?
That is up to you. I could show you. So let's go back to, so this is our model. So if I'm done and I hit save, and we'll do this actually, Brian, because what we'll do next is create a model from scratch, and just to see how quick and we could do it. And then I'll show you at that point.
Well, let's do that. That's okay.
Yeah. So if I go back to my slide, you know, that's sort of what I have here. So, you know, demonstrating the speed and ease of using WikiModel to solve a problem. So I already have an account, but to all of you, obviously, you do not. So I would encourage you to go to, you know, you can go to WikiModel right now. If you go to wikimodel.com, and I'll sort of semi do that. So let me open it again here. So it automatically logged me in. That's kind of cool, is once you log in, it remembers you. And so you don't have to log in every time, you know, every time on your browser, because it remembers you that you logged in before. But let's say if this is your first time on the WikiModel page, what you'll see is, you know, it'll let you sort of look and load, but as soon as you simulate something more than once or twice, it'll ask you to log in or register. So let's say you're new, it's your first time here. What you want to do is you go to wikimodel.com and you hit register. Actually, I think what happens yeah, so if you go the first time without doing anything, it'll actually automatically bring in this login pop-up window. And if you don't have an account, you just click here, create new account. And I'd encourage you to do that now. If you know, you don't have to, I'm not going to force you, but if you're interested in trying out WikiModel, I think it's a good time now to go to wikimodel.com. And then when you get this pop-up screen, click on create new account. I will say that if you have a Gmail account, you can log in with your Gmail credentials, and you don't have to register for a new account. It'll just let you log in with your Gmail login. So, but I'm gonna, if you're in academia, I'd encourage you to do it with your institution's email, because then when you work with your students, you can sort of get all put into a group all together, and it sort of makes it easier that way. So click, if you if you'd like to, I think now when you get this pop-up, hit create new account. What you'll see is you'll ask for your first name, last name, email address, and what password you want to use. You would enter that password in twice to make sure you typed it in correctly. And then this should say register, not registration. But then you click on this register button. And once you're done, it'll send you an email to the email address that you typed in. And then when you get that email and you click on, it'll send you a link in that email. You'd click on that link and then you can log in. So I would encourage you to do that now. I'll give you some time now to do that. And then maybe we can, work on the model together if you're interested. So go ahead and do that. I'll probably give like a few minutes for you to do that. I mean, I could create a new email address and start from scratch if do you think that's a good idea, Brian, or should I just wait for folks to try it out and see if they have
Just wait, and we're going to assume that you're going to simulate all that they might do, even if they're not logged in, right? I mean, you're going to build from scratch, and so they'll follow that. And by the way, you're going to save that as public.
Yes, if you want to.
Well, yeah, and so that they can say, that's the one I want to look at.
Yeah.
It's the prototype.
Yeah.
Okay.
I've actually already implemented, but I'm going to implement it again. It's already there in the library, but I'd encourage you not to load that one because we're gonna not to load it right now because we're gonna try to do it from scratch. So is anybody trying the login? Let me know if it trying the registration for procedure. Let me know if that works out or if you're having any difficulty. I can help you.
Well, why don't you go on and let's start from scratch.
Okay, sounds good. So to start from scratch, let me. So I'm already logged in. Let me log out and re-log in. So what you want to do is you first log in. I'm going to type in my email address. And log in. And when you log in, it sort of automatically loads in one of the pre-saved publicly available models, and it loaded one. But if you want to start from scratch, you would go to this this drop down on the top right where it says workspace input output, and you type, and then you would click on new workspace. And when you do that, you have sort of on the right-hand side is what you're working with. The left-hand side is just sort of the library of available models. The left-hand side is sort of where you're doing your data, entry, and you'll see that it's blank. There's no models, there's no parameters. So let's talk about which model we want to simulate from scratch. Again, this is a model that describes the it's the Torricelli model, and it describes falling water in a column with a hole in it. So again, I got this from the Simiode website, and this is something that Professor Winkle wrote up, and he's got experimental data where he's got time and the height of water in the column. Let's see, I think you had a good picture also. The picture might be on the website where you have, the experimental apparatus. But I think it's here, but I think there's another picture on the website. In any case, the ordinary differential equation in the model is described in the document. Here it is. He's got the differential, the rate of change of height is proportional to the height at any point in time, and there's a gravitational term and so on. So what I'm going to do is let's go to the page. So my independent variable in this model is time. I'm going to just call it t for time. T for time, and I'm gonna start at 0 minutes and go every minute, simulate it every minute up to 70 minutes. I'm gonna do that. Okay. Then this is a model with just one equation, and the equation is the rate of change of height. So to type in differential equations, you need a d dt. So in this case, I'm doing dh dt is equal to minus b times the square root. Now, square root is sqrt. You can also do to the raised to the power, shift 6 to the 0.5. But since square root is a function that's available, I'm going to use that. But you can do to a third power, to the any power you like. So I'm going to do g times h. So there's my one equation. Now what you'll notice is as soon as it recognizes that you've typed in a differential equation, it's asking for the initial condition. So the initial condition is the initial height of water in the column before you unplug the hole, right? So let's get that from here. So if I find the data that was in that table, so let me make this bigger so I could see it better.
By the way, that table comes from online source. I don't think that's what I collected.
Ah,
but
okay.
it doesn't matter,
Yeah.
So go ahead.
Yeah, so what I'm going to do is sort of move this over to my other screen. Okay, so I'm going to move this over. Okay, well, actually, I bring this back up here. Okay, so then we'll go to this data tab, and there's no data, there's nothing here. So what you want to do is you say, oh, I want to add a new data variable, and I'm going to call whatever it has to be called data underscore. Your independent variable has to be data underscore, and whatever you call the independent variable in the model simulation for the independent variable. So in this case, it has to be data t. So I'm going to hit enter. And but I also need to add the height. So I'm going to do add new data variable. I'm going to call this data height. Height. I always like to have a prefix data, but you don't have to except for this one. And again, it's data underscore. Remember, our independent variable is t. So the first one has to be data t. So, but I still don't have any data points here. So what I have to do now is I say, oh, add new data row. So my first time is 0, and my first height was 0.35. I think these are all in meters for me here. So 0.35, and I've got add a new. So but my next time is at 8 minutes. Is it 8 minutes or seconds? 8. I think it's seconds. That makes more sense. So 0.3, add new row. I don't think it matters to put the 0, but I'll do it. So then we have 16 seconds, and it's 0.25. Oh, we've got 25 seconds and 0.2. Add new row.
By the way, as Sammy's doing this, we do have at Simiode, we have YouTube channel, which has videos where you can stop and start for various configurations and openings and collect your own data, or you can spill water all over your office desk and collect your own data.
So I know that entering in the data is cumbersome. What I will say is you can actually, if you have the data in a text delimited file, you can upload it. You can upload it from here. I won't go into that here, but you know, if you already have it, you don't have to retype it. If you already have it saved somewhere, you can upload it. But I don't, so I'm going to do it this way. So 66.8. 8 and 0.05. Okay. So now that we're done, we could go back to the model page and see, okay, here's our equation. Now, the one thing let's say I've got two parameters. I've got two parameters, B, and B I think is sort of some constant that's related to the hole size. And H is your variable, so that's fine. Now you do have G, so let me add the parameter, parameter B. Now I do have G, so the question is, do we make G a parameter or do we make it an equation? So why you would, what's the difference, right? So if I'm sure of a parameter value and I don't want to fit it to my experimental data, then we should add it as a constant as an equation instead of a parameter, because when I hit fit, I don't want the program to fit G. I already know G is 9.8. I'm not going to allow it to change that. So I type in G equals 9.8. Now I do have to define G before I type in that equation, because that equation is dependent on G. So you can drag this and move it up. Okay, now I do need to type in my initial condition. So I need to get my initial height from the data, and that's 0.35. So I'm going to copy this and go here and put it as my initial condition. Now, if I hit simulate now, it's not good. Well, first of all, I have to give a parameter value for B, a non-zero parameter. So I don't know, let's give a 0.05. Right? So now I just want to show you, if you simulate this, it's not going to work, because in order to simulate something, you have to say that you're interested in plotting at least one output variable or one simulated variable. So if I hit simulate, it's going to give me an error. It says there must be at least one plot in the model. So what you then have to do is go to plots and say, hey, I want to add a plot. I'm going to add, and it's going to be on the top graph. I want my x-axis to be t and my y-axis to be h for height. It just plotted this sort of randomly from a previous thing. So now if I hit simulate, you'll see that here's my height that changes over time. So, you know, if I change this number, let's make it 0.001. I can then say, if I change that B term to 0.01 and I simulate it, it takes longer for the water to fall out completely out of the column. So what we're missing here is the data. So let's go back to our plots and say, hey, I want to add a plot, which is the data, but I want to plot it on the same graph. So I'm going to change this graph number to 1, and I'm going to go, my x in this case is data t, and my y is data height, because that's the data, you know, that's the variable names in the data table. So, but in this case, I don't want to, I don't want to connect the lines. I don't want to connect the data points. I just want to plot them as open, as closed circles. So let's make the point size, you know, 5. And you can see there's the data, but I don't want the line. So I'm going to go 0 here. And I want to make this, I like to plot my experimental data in black. So I'm going to change the color to black. And, if I want to change the gray to some other color, like blue or green, I can do that. And there it is, right? Let's make it a little darker. Right, so now we could say, oh, well, it should take a little longer. So let's go to here. And let me take a look here. So we make this number smaller, it should take longer according to this equation. So let's just try 0.005. So hey, I'm getting closer. Let's try 0.006. Oh, whoops. No, I have to go smaller, not bigger. So 0.003. Let's try that. Okay, so now I've overshot. So now let's say I don't want to keep guessing. Let's try to fit the data. So before you fit the data, you have to say what you want to fit. So I want to fit my H to data height. So I have to go here. I have to pick H. And I have to pick data height from here. Now I can hit fit model and let's see what happens. And boom, it goes right through the data. I mean, it's not perfect, right? The data has, there's always noise in the data and there's always imperfections in the model. So your error is never going to be 0, but here it's got, it's telling us that, oh, the H value is 0.0036, and 16. And if you want to look at the error statistics, you can go to fit statistics and it says, oh, my sum squared error is pretty small and my R squared is really high. And, I fit data, I fit 7 points and I'm fitting 1 parameter. So I have, the difference is the degrees of freedom. So here's your error statistics, which you have. And it tells you that it's doing nonlinear least squares. If my equation was just a line, it'll just give me it'll just use least squares and give me that. Or a polynomial it's still, even though polynomials are nonlinear, it'll figure out that, oh, I can use least squares to fit the coefficients. But anyway, back to this model. So you can see we typed in the equation. We've got some constants in the equation that has to go in first. And we type in our parameter name, our value, and we could simulate that and then fit it as well. But you have to make sure that you type in the right things. If you type in the wrong thing, it won't work. So if there was a typo in square root, so what I'm working on right now is having some feedback so that if the user types in an error in a particular equation, it'll come back and say unsuccessful because you have an error in, line number 2. Right now, it doesn't do that. And I realize that is a missing feature that would be great to have to give feedback to the student. And I'm working on it. I'm hoping to have it in the next month or so. But let's try what happens if you, instead of square root, you typed in you typed in, a Y instead of that, and you try to simulate this, it's gonna keep doing this and return with nothing. It'll eventually time out and give you a 0 plus. It gives you a nonsensical result. So if we fix it, and it works again. So I'm working again on giving feedback so that if you type in nonsense, it doesn't just return a flat line. It just tells you that you have an error. But if you get flat lines, you know that it's not working. Are there any questions about this?
Can you hit the fit model button again? Because I feel uncomfortable. Oh, that looks much better.
Yeah. Yeah, so and then you can export. What was your question? Oh, you asked about saving it, right, Brian?
Yeah.
Yeah. Okay, so when you're ready to save it, and you can save it intermittently before you're done, but you do have to have one variable in the plot, I think, if you want to save it. So when you're ready to save it, you hit Save Workspace As. Right, and so what do you want to call the model? Let's call it waterfall. waterfall, okay. And then I can give it a category. The category can be anything. I suppose I could have limited it to a pre-selected drop down of options, but I don't know, what should we call this, physics or fluidics?
Yeah.
Fluidics, right? But you also have data. You also have a data set that you created. So let's give that a name. I'm going to call it waterfall 1 or experiment 1. And you have to give it a description. You could say this, this is, I could call it the same thing, waterfall. Okay, so now when it comes down to permissions, you can either do private. Private means only you can see the model and access the model and play with it. It's only for you. But the cool thing is you can, you don't have to lug your computer around, remember, because we didn't download anything. We just went on the website. So if you can create the model at home and then simulate it in your classroom and with your school computer, right? You don't have to, if you had to download the software, then you'd have to carry the laptop with you, whichever one that you use to download the software. But since this is running on the cloud, you don't have to. You can even run this on an iPad or a phone. I don't recommend using a phone because the screen is too small. But the point is it's agnostic to your device and your operating system. So
But
anyway,
if you wanted to run this for this group, right, and we were identified as
yes.
a group project, we could do that, right?
Yes. Right. So I could do this. I could say, I want to save this as a group. Now, I created a group called group 1. I forget who's in it, but before you could save it as a group, you have to first create the group. So I'm going to show you how to do that. So for now, let me save it as private or private.
Public.
Okay. So when I do that, I hit Save Workspace. Now, let's say I re-log in for the first time. I'm going to log out. And log in again. I have an IBM touchpad that wants me to use my fingerprint. Okay, log in. Oh, it loaded it because that was the last one I had.
Yeah.
But let's just let me just load let me load a different one first. So let's say I was playing with another model and I wanted to find my waterfall one. If I knew what I called it, I could just type it in. Or if I just remember part of it, I could type it in. So I could just type in water, type in water, and I hit search. Oh, look, it found waterfall. It's a category fluidics. I created it on April 9th, and I haven't modified, I last edited on April 9th, but you can't just hit load first. You have to select it because there can be multiple ones with the word water in it. So you have to choose it till and then it's blue. Then you hit load selected model, and then boom, here it is. It brought it back up again. Let me hit fit it again. Yeah. So do you want to, Brian, should I show the groups thing?
No, I just wanted to add for those of us who are teachers that, so supposing you had several graduated cylinders, each with a different size hole, okay, and you collected data sets, you might be wanting to explore what's the effect of draining the water with different size boreholes. That might be the civil engineering project. You have a pipe, you have a hole. If you double the size of the hole, what does that do to the drainage rate and so forth? So this software will allow you to explore that exhaustively and beautifully, I think, and store it and report it. And by the way, can I grab these plots and put them somewhere in a document? Is that hard to do, Sami?
Well, so right now, like how I showed before, you can download it, right? You download simulated results.
Gotcha. Okay.
Yeah, and I showed that right before.
That's
you
fine.
could-
Yeah, okay.
I mean, or you, it's kind of, it's not, I admit the quality of these plots aren't that great. So I always like to download them and put it in another program.
Okay.
So yeah, that's how you would do that.
But what I'm saying is I'm hoping that as you are in our group here, you look at this and you begin to say, wow, I could do this and I could do that. And then that you go and try that. And I think you'll find it quite rewarding and students will find it easy. And that's why we asked Sami to do this for us on our behalf. So we've got about 10, 12 minutes. If you want to talk about we're going to talk about the groups. Is that? Because,
I put, rather than do that, why don't I bring up the instructions? Because the instructions talks about the groups, it talks about everything really. So why don't I bring that up? So if I go to, if you see the webpage, you can hit, let's see, where is it? About, you could go to WikiModel application instructions. If you click that, I think that's a good place to end. So when you click that, it shows you sort of how do you log in, how do you select models that are already there, how to create a new model. That's the process we went through right now, so I won't dwell on that. Here's how you type the equations and where the results of the fit. And how this is talking about how you can upload the data if you already have it in a text format, text tab delimited format. You can even upload, if you can even type the model equations in your text file and upload that. Here's your independent variable. You can type it in your data. And what you can do, if you want a template of this and you wanted to type it in offline, you just, when you go to your model, you just download your workspace and it'll create this file. So you can then edit the data and upload it again if you would like to. But here's a list of all the functions that you can use. And you can even do, I didn't talk about this, you can do conditional statements in your model that, if a criteria is satisfied, then the value of a variable is equal to some number. But if it doesn't satisfy that condition, it's equal to another number or expression, right? So here's an example of that, right? So if t is less than 1, then the value is -2. If the value is, in a different range, it has a slope, and so on and so forth. So you can use that. Here I talk about, I can interpolate, I can have a variable that's based on interpolated values from my data table or impulse or a step. So, here's my interpolation, here's my impulse, and here's my step function. So the reason why this is important is in a lot of simulations, you would input your drug as a set of impulses like injections, or if it was a pump that was a continuous infusion, you would use a step as your input function. So there are examples that describe how you would use those. Where are the groups? So, here's an example of pharmacokinetic model, which we just did with LSD. This is a different example. Here's the saving, right? Here you could save it as private, public, or as a group. Here's the, here's creating a WikiModel group. So you go to My Groups and you follow these steps. If your students have registered, you can find their names here and add them to your group. One other thing I didn't show is, let's see, where is this? So what you see here is there's an about current workspace. You could see you have a direct link here that it creates. So if you send someone this link and they click on it, they can go to this model directly instead of trying to find it. But you can also add a description. You could say this model describes the rate at which water falls. And you can add a bunch of things. It's in rich text format, so you can bold type it. You can upload an image. So if I wanted to, get this image, I can upload it Of course, I don't want to get into copyright issues. So if it's your image or if it's a public image, that's fine. You can upload an image. And people can write comments and people can like your model. You know, I can click like. So I guess we're getting close to the end, Brian. I did have some more slides that showed other examples, but I don't think we have time. I would rather just use it for questions.
So one other thing you can, if you have 4 students working in a team, they can have their own space, right? They can work on a project as a group, right?
Right. Now when each student saves the model, they will get their own individual copy of it.
Gotcha.
Yeah, that's how that works currently. So and I did that intentionally because I didn't want my data or my results to mess yours up, the original creator, right? Because I don't want if the teacher created it and the student changed some numbers, I don't want the teacher to go back and say, hey, what happened? So it'll be, you would have to, each user has their own copy of the model.
Okay. All right. Are there any, comments? Anybody want to volunteer whether or not they think they could use it, how they might use it? Any conversations that we want to initiate? Please speak up.
Okay, this is France. Do you hear me?
Yes, we do.
Okay, thank you very much for this presentation. I thought it was very nicely paced. I see a lot of similarities with the Insight Maker environment that we will see in one of the forthcoming workshops, webinars. And the main differences here being that first, you write your own equations, whereas the Insight Maker is more icon-based, where you directly work on the compartments and the fluxes, the stocks and the fluxes type of metaphor to illustrate to build the model. And the other major difference is this fitting functionality that I find both empowering, but at the same time, maybe too, maybe it reduces the opportunity for the student to get the intuition of the parameters first. Like if you have to go on trial and error, it may be a bit, it may be worthwhile to play with the parameters first before getting into the fitting already.
Sure, and you can do that. You can.
Yeah, I understand.
Yeah.
But I find it powerful, and I'm glad that they also supply, make it explicit what optimization or regression scheme they are using to optimize those parameters. In the same way that they do also mention which, and this is an option also for the user to select the integration method that is used.
Oh,
so,
right. I don't know how you figured that out because I didn't.
In advanced setting.
Yeah. Oh, so you logged in then?
Yeah. Yes, I did the whole
okay.
shebang.
That's good to hear.
So you see that, Sami, people pay attention.
Yeah.
Yeah, we are discreet, but we're continuously listening.
Oh, thank you.
Thank you, Francis.
That's great that you're able to log in and see the features. That's great. I'm happy to hear it. At least I got at least one user, one user.
So what do you think? Think you might be able to use this in your teaching, get your students to use it as an option, an alternative?
I'm more thinking in terms of teacher education, and I would find it a nice step up after Insight Maker, because I think you might, it might be more efficient in some way. I would have to see how you can input the data with a direct CSV or Excel file to make it worthwhile if it's not as cumbersome as entering one. But I assume, as you said, you can do that just as you can do that in Insight Maker as well. So that is. So yes, I think it builds well from. Maybe a nice step up from Insight Maker.
France, are you teaching high school teachers, or are you teaching, what is it that?
that I've tried, like I'm a retired educator, but I still work with teachers as a hobby. And and then I also have students that I'm supervising in that direction as well. And I would see it more for the, what we call here in Quebec, the cégep layer, which is just between high school and university. So it's like the last year of high school and first year university, where you get introduced to calculus. So in the once you've looked into, often people say, well, once you've done differential and integral calculus, you can get into that type of thing. But sometimes I wonder if we could not revisit that order, taking into account the tools that we now have to build the intuition from discrete models up, because it's easy to describe a flow and integrate the flow. People can understand that with a bathtub metaphor, and it might be worthwhile to rethink these things sometimes.
Well, Sami, why don't you tell us a little bit about some more examples, and then we'll thank you and we'll all go on our way.
Yeah, it's already 5. I'm happy to stay on as long as necessary, and so I can go through an example. I will say for France and everybody here, my email is Sami@wikimodel.com. It's SAMI@wikimodel.com. If you have any issues or problems or questions, I would love to hear from you. So you can go ahead and send me an email with any questions or concerns. So I did highlight a few models, that some of which I just created out of interest, some of which I created and presented at other presentations in the last couple of years. So is there anything here that somebody would like me to, to bring up of these examples? Is there one that's interesting to anybody that that you'd like me to bring up?
We can see all of these, right? If we want.
Right, you can just click on the links, but like I said, as I said at the top, don't scramble and write things down. You can just, if you just type in part of the name and you can use the search bar, it'll bring it up. So I don't know, is there anybody have a choice, or I'll choose if nobody picks one.
Well, we're just about out of time, so I don't want people, but if people wanted to, if you look at, say, the type 1 diabetes, I mean, or any of the compartment models that'd be similar,
Yeah.
That give people an idea of how, maybe I should ask, how complex can the models get? How many equations have you?
It can be, I don't have a limit on the equations. So if I bring up this, electrocardiogram model, so here's my electrocardiogram model, and as you could see in the slide, I actually found this model in a IEEE publication. I just took the equations directly from that and I typed them in here. And you could see there's only 3 differential equations, but there's a lot of dependent analytical equations that plug into these 3 differential equations. And so, there's quite a few, the one we did had, 1 equation and there was 1 constant. So there were 2 lines, but this has a lot more than 2 lines. And here's my, let's see what happens. It's asking me, why am I not logged? It's asking me to log in again. Oh, I think it's because I have my other Chrome browser open. That's why it usually doesn't ask you to re-log in if you're already logged in. So here's my simulated output of this ECG electrocardiogram output, which I thought was really cool. And there's a lot of parameters here. Look how many parameters there are. I don't know which one you want me to change, but there's way too many to play around with. I wouldn't fit a model with this many parameters, but it's really cool. The author did fit some of these parameters, and so it's not that this is totally just made up. It actually replicates clinical data as well.
Okay. And one other question, France alluded to this as well. do you state your algorithm for optimization for the minimization in the?
No, I don't. I just, well, I just specify whether it's a nonlinear least squares or a linear least squares.
Okay,
I don't, it's a Nelder, I believe it's a Nelder-Mead least square, the nonlinear least squares algorithm. I will do one last thing. Let's see, that I have a polynomial fit that, let's see, that shows kind of, see this polynomial. So a polynomial is nonlinear, but the coefficients are linear, right? Because
Yeah.
you're not fitting the exponents, you're just fitting. So let's see. So if I have this data, I just have y equals ax squared plus bx plus c. And I've got my data points here, just like I did before. Now if I hit fit model, it says the fit completed successfully in 0.002 seconds. And if I go to my fit statistics, it says, oh, my fit type here is linear least squares. So that I think is pretty cool, that it can decipher whether to use nonlinear least squares or linear least squares, depending on the nature of your model or equation.
and then finally, you use this in your professional work now, right?
So I do. I consult for a biotech company, and typically what I'll do is I'll sort of see the feasibility of different models for my work. And then but then for my work, I'll run it on like 100 data sets or 1,000. So then I'll take the model that I came up with here and then implement it in code, because I can batch run it, or I will, I could call the API, but usually I'll just write it in code, in Python code, and do it. But what this allows me to do is to try different equations quickly and to see if something's feasible. And if I think it's reasonable, if it's reasonably feasible and looks good, then I will go ahead and implement it in another tool if I have to batch process a whole bunch of data.
Well, I hope our audience believes that they can see how their students could do this. We already demonstrated it with the falling column of water, and you've demonstrated it with some data from the literature. Students are encouraged to collect their own data. They can build the model. I mean, this is a complete opportunity, and I'm really thrilled that you've done all this work for us. And I want to encourage people to keep in touch with Sami to make sure that they can access it, and by all means play with it. I mean, it's like anything else, right? The more you play with it, the more you become convinced. Again, we'll have the video. We'll follow up with a little survey on some questions concerning this and the value of this to you. And we thank you very much for coming. And if you have nothing to say other than goodbye, Sami, I leave it up to you to close.
Yeah, that's great. If there are no other questions, I appreciate everybody's time, and thank you again, Brian, for the opportunity, and Lee for organizing.